Okay, let's get started. Let's get started. Ready to start. Have your attention, please. Okay, so I have updated Blackboard. Here's some real important announcements. Office hours and tutoring. Okay, there's this right here. Office hours and tutoring. So this question will come into your mind often throughout the semester. When are your office hours? 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 They're all here, okay? There's me, there's Kirk, and there's Roy, and then there's a whole nother set of people that you can go get help from. Stacy Musgrave, Cameron Byerly, Annie Didier. Cameron is a woman, okay? So this is Stacy, Cameron, and Annie. The office hours are here, and they're kind of spread out all throughout the week. There's only a little overlap here, not much, okay? Let's see. So this we're going to talk about how this course is very different than maybe math courses you've had before. If you go to just a generic tutoring center, a math tutoring center on campus, or you hire a math tutor, they're not going to be familiar with this. 99% chance they will not be familiar. Everybody on this list is very familiar with what we're doing. This is definitely, by far, your best way to get help. So if you hire a tutor, if you go to some just generic math tutoring center, you're not going to get the quality of help that you will hear, okay? And we're providing 6 people for you with office hours all week long. So this is free tutoring. Free tutoring, you just may have to wait a little bit, okay? You're going to need to take advantage of that. Okay, so the homework. Come on. So the internet's going to work good today, right? Hopefully. I have put this format for written work right here at the beginning of the readings and homework section. So get your homework out, and I'll show you what we're going to do all semester. We're good. Ready? Ready. This is the format that you need to follow. If in some ways you don't follow it, you can get voice deducted, okay? Here we go. So you're going to take it facing yourself, put all the sheets together, and you're going to fold it right down the middle. Vertically. Got a sheet of paper I can borrow? Okay, so here's all your homework like this. You're going to fold it vertically right toward yourself like that. So if you didn't staple today, it's okay. Now all of them will stay together. So, but in the future, staple. If you did, okay, then you're going to turn the open sides to the right. You're looking here. Here's the back of your staple. Here's the back of the last page. That's where your heading's going to go, and this is the heading. You're going to write your name. You don't have to write the word name, and you don't have to do it diagonally. Okay? Do it straight, and just write your name. Write your recitation, which is either Wednesday or Friday, 10:30 or something. 10:30. 10:30 or 12, so whatever your recitation is. And then today's date is the 15th. Is it the 15th? Yes. There you go. But that will, obviously that will change. Okay? Make sure you have, there's a nice clean left edge, no fringe. Okay? So when we have over 100 papers that we're collecting, and there's fringe on the edge, it makes a mess, and it's hard to work with, okay? So with lots of people, that makes a difference. So get either clean left paper or tear off the fringe. And then when you do your homework, so this if you didn't quite follow this, it's okay the first time, but you want to leave space for the grade up top. You want to identify your problems clearly, use indentation, use vertical space between different problems. Be professional and complete, and you can see more details on the syllabus for that, okay? So if you didn't follow this, that's okay, but now from here on out, whenever you do written homework, these are the expectations for the actual content, and then this is how you're going to fold it and do the heading, okay? And that will be posted all semester long as the first post in readings and homework, and so you can find it 24/7. If you forgot how to do it. So then just have that ready when you come in that day that written homework is due. Questions on that format? Got it? So let's collect. How are we collecting today? Maybe let's, that might, should we pass? Or do you want to do it by day or, oh yes, okay. So if you're in Wednesday, you want to go which way? If you're in a Wednesday recitation with Kirk, you're going to pass left to the end of the row, to the left. If you're in a Friday recitation with Roy, you're going to pass to the end of the row on the right. Keep them all oriented the same, stacked on top of each other. Thank you. Okay, so while you're doing that, if I could keep making announcements, that will help. So if you can listen still. Okay, I'm going to keep making announcements. Okay, so no talking. So you just pass without talking? No, please. I don't have an extra. I'm sorry. Okay, so the next thing I want to point out is, if you didn't catch it, I will make a screen recording and a class video of every class. So those are here on Blackboard. This is going to be a huge resource for you to reinforce and retain what you learn in class. So often you'll come out of class, I hope, and you feel like, oh, I got it. 90%. Makes sense. I got it. But with all the other classes you're taking and all the other activities you're doing, within 6 hours, 12 hours, it will fade. Trust me. Okay, so it may make perfect sense or mostly make sense when you're walking out of class. It doesn't mean you're going to remember it a day later. That's what the videos are for. So they're on YouTube. We are recording right now. So this is an excellent resource for you to retain the information, reinforce the information. Okay? Use the videos. Okay, talked about the GC graphing calculator software. You want to start this weekend, get it downloaded on your computer. And so on Blackboard announcements, there's now the second announcement down here, is how to download graphing calculator. So if you're going to download it on your Mac, it's the first link, the Windows the second link, there's some instructions. Then the registration info, I put it twice. Okay, that's what you need to get your free copy of Graphing Calculator, which we will call GC, Graphing Calculator. Okay, you will be working on this in class. You'll be doing assignments on this as a required element of the course. So make sure you get it downloaded this weekend. Okay, and I'll be using it as a teaching tool, but then we'll also be using it. You will be creating things as a learning tool. Okay, questions on that? Okay, the homework for next Tuesday. So unfortunately, I don't know what your opinion is, but the truth is, it's unfortunate that we only have 2 classes a week, and we give us 5 days in between. And that's not the optimum way to learn intense material like this. So that means I don't see you for 5 days. That means you're going to be doing lots of work over those 5 days. So here's the next set of homework. It's from 3 different readings. There's this first reading that you're going to finish up the work in that first section. I posted 2 more sections. Again, please read very carefully exactly what's expected. Just because I post a document doesn't mean I'm asking you to do everything in that document. So you're going to finish what you didn't do in the first section. You're going to do everything in the second, and then the first part of the third. Okay? Don't wait till Monday. Don't even wait till Sunday. Get started on this. There are lots of, in the office hours, there's lots of availability. There's like 3 or 4 different people available on Monday. So work hard on this over the weekend, and then come get help if you need help. This section 2 and 3, we are not going to talk about in class today. It's somewhat prerequisite material, and so it's going to be you're going to be reviewing or self-teaching, self-guided learning, okay, through the reading and those problems. But then if you need help, then Monday office hours, okay, or even tomorrow office hours. You can get started on it tonight. Questions on homework? So carve out time, several sittings of time. You're not going to sit down, like I said, on Monday night. I got 3 hours on Monday night and crank this out. It's gonna take several sittings.
Oh, will we have to print that out?
The documents?
Oh, like the problems.
No, this is written homework. You didn't like what you turned in today.
Okay.
Yeah, you're just doing written homework like you turned in today with this format here.
Okay.
Yeah, so you're not going to print it out and write your solutions in there. Although in some places you could, but you're going to turn it on separate paper.
Okay.
Yeah.
I see.
Other questions? Okay, so we covered office hours, homework format, class videos, graphing calculator download. So I'll actually include that. Part of your homework is to get graphing calculator go up and running on your computer. That'll be another task for Tuesday. Okay, Top Hat. Let's do Top Hat. So get your internet going. So remember that. Here's our summary for multiplication. So these bars normally represent the values of two quantities. Scaling is about resizing a quantity to a new value of the same quantity. That's like the water evaporating. 0.3 W now is the new amount of water. It's a shrunken amount of water. That's scaling. Constant multiple is about finding the corresponding value of a different quantity. So these are two different ways that we see multiplication in use. Okay? And we're going to find that constant, in terms of learning the calculus, constant multiple is going to be a really key idea in learning calculus. Okay, questions on multiplication? If you missed those on the top hat, does it make sense now? Keep reviewing that. Okay. So what about this? What operation has the result of the relative size of one quantity in relation to another? Yeah.
Division.
She wants division. Agree? Should have read that in your. And like we talked about, the division is one of the key operations of calculus. And understanding that a quotient, the result of division, is relative size. So let's see how that plays out. We've got building A is 17 meters tall. Building B is 5 meters tall. So building A is 17/5, 3.4 times as tall as building B. So let's kind of see how this plays out. So this is like a bar diagram, but we just turned it up on its side so they look like buildings. And so one of these little squares is 1 meter. But what's another way to say what one of those little squares is? What is it relative to B? The whole height of B. 1 meter is what relative to the whole height of B? 1/5 of B, right? And then how is the height of A determined by squares? How many squares or how many meters? 17. So the height of A is 17. You could say 17 1 meters or 17 squares. And each of those squares is 17 1/5 of B. Or 1/5 of the height of B, I should say. Is that a fair statement? So the height of building A is 17 1/5 of the height of B. Okay, another way to say that is the height of A is 17/5, right? 17 1/5 is 17/5. So here's where division's coming into it. The height of B. And 17/5 then is 3/4. So what, or 3.4, sorry. So we're asking, what does that number 3.4 mean? 3.4 is a quotient. It's 17 divided by 5. So what is the meaning of that number, 3.4? What is the meaning of that number? It's a size. The size of what? Size of building A. It's 3.4 meters? No, 3.4. Yeah, you can think of it as times the height of building B, or 3.4 building Bs, right? It's like measuring the height of building A using the height of building B. So if we were to use building B to measure building A, it would be 3.4 Bs. This is the idea of relative size. A is 3.4 relative to B, the height of B. And like you said, the height of A is 3.4 times. So the idea of relative size then goes back to, so we can do one more statement here. Height of A equals 3.4 times the height of B. So now, in talking about 3.4 as this quotient, as this relative size, we ended up with a multiplication. What is 3.4 in the multiplication? What does it represent? What is it? It's a constant multiple, because it just gave us the magnitude of one quantity starting with the magnitude of another. So the relative size, this idea of relative size and constant multiple are like very close cousins. Very close cousins. The result of a quotient of two quantities, the values of two quantities, then becomes the constant multiple of finding the value of one corresponding to the value of the other. But this idea of relative size, it's like measuring one quantity using the other quantity as its unit. How many building B's make up building A? 3.4 of them. Therefore, the height of A is 3.4 times the height of B. Again, so this relative size, the quotient, very closely related to the constant multiple reasoning for multiplication. The relative size is the constant multiple. The relative size is the constant multiple. Okay, so let's look at rates. So again, the quantity, the result is the relative size of one quantity in relation to another. Division, a car traveled at a constant speed. It traveled 1829 feet in 19 seconds. How many feet did it travel each second? So can you use a bar diagram to analyze this? Set up a bar diagram, analyze to figure out if it goes 829 feet in 19 seconds, then how many feet did it travel in 1 second? Set up a bar diagram. Get out your whiteboards. So make your work relatively large so that we can see it. We don't have to get real close to see it. Only a few people are labeling their bars on the left with the quantity that it represents. That's the first thing you should do. The first thing you should do is label those bars with quantities that they represent. And then put the numbers on. remember these are just a tool to help you think about the quantities, okay? Yeah. Let's talk about it later. Okay, so how is the bar diagram helping you do that? So you may have an idea just how to crank out the answer. So drawing a bar diagram and then cranking out the answer separately is missing the point. How can you use the bar to reason about it rather than just, oh, I know how to do this. I know how to do this, so I'm just going to do what I've learned before. Okay? Okay, so if we want to know how far we go in 1 second, how can we use the bars to talk about that, or use the bars to analyze, kind of make progress on that situation? Yeah. But we're using the bars, so it's not just about doing a calculation. So we're making the bar diagram and then doing a calculation. It's about thinking about the bar diagram. How can we've got 829 feet corresponds to 19 seconds. So, okay, so you're looking at the 19. Okay. Okay, right. She said she wants to divide the bars into 19 equal parts. So, yep, so really, it's really about, yes, 1/19 of the 19 seconds bar is 1 second. So 1 second equals 1/19 of 19 seconds, right? So that's what she's saying. She's saying, let's divide up the bars into 19 pieces. So then how do we get the distance traveled in 1 second? It can be 1/19 of the distance traveled bar. How do you find 1/19 of 1829? Yeah. So many of you, when you saw the question, you might have come up with this just in your head right away. But what the bars is showing us is, why is that true? The bar gives us kind of an explanation of why is it that we divide 1829 by 19. Why? Because we need 1 second, which is 1/19 of 19 seconds. Therefore, we want 1/19 of 829 feet. And so that's what that fraction is doing. It's giving us 1/19 of 1829. So what kind of operation is that? Yeah, so this is why you divide distance by time, because what did we just calculate? What is this? That's the speed, right? That's the speed. So calculating speed, this is why it's division. Okay, because you're going to take 1/19 of 1829 feet, just like you're taking 1/19 of 19 seconds. Okay, so if it's a division, if it's a quotient, and that equals 96.3, by the way, feet per second. If it's a quotient, then it's a relative size. That's what we said. So, how can it make sense as a relative size? Talk to the person next to you. How is the number 96.3? How can you make sense of that as the relative size of one thing in relation to another? Go. Talk to the person next to you. How can you make sense of that as a relative size? Should be 60 people talking right now. Remember, 60 people should be talking. Okay, so 96.3 is the size of what? Volunteer, who can? If it's a relative size, then 96.3 is the size of something. What is it the size of? Or the magnitude of? Adam? Okay, does it have to be one? So it's a relative size. So he says distance traveled. Is it an amount of distance traveled, 96.3? Okay, so relative to what? How much time goes by, right? Does it have to be 1 second that goes by? What if 10 seconds goes by? How many feet did you go?
963.
963. So that relative size is maintained, you see? In 10 seconds, you would go 963 feet. So the relative size is still 96.3 because the distance you went was 96.3, what? Times as much as the time that went by. Remember we said there's this very close relationship between relative size and the constant multiple reasoning. So if 96.3 is a relative size, that means the distance that you go is always 96.3 times as much as the time that went by. It's a really crucial thing to understand. So it's the relative size of distance traveled with relation to time elapsed. Distance traveled with relation to time elapsed. Whatever time elapsed you have, the distance traveled will be 96.3 times as much as that. That's the idea of relative size. Okay, so how can 96.3 be thought of as a constant multiple in this situation? We just said it, yeah.
96.3 times 19.
Does it have to be 19 seconds?
No, time.
Any time, right? So any amount of time, we know that the distance will be 96.3 times as much as that. Its value will be in feet, will be 96.3 times as much as the amount of time that went by in seconds. Again, they're close brothers. Relative size, the result of a quotient becomes the constant multiple. Yeah?
So they're basically the same in terms of the idea?
Well, constant multiple is focusing on it as a multiplication, as a way of reasoning about multiplication. 96 relative size is thinking about that as a quotient, but they're very close. They're like brothers. They're like brothers. Okay. All right, so we're going to skip that one. So, you've had a little taste of what we've done so far, right? So we had Tuesday's class, we had homework, we just talked about division here. So, are you thinking this? It's different, right? This is really, really different, okay? Or for some of you it is. So let's talk about a perspective on this course. I want to emphasize and give you kind of warning for what the semester will be like, so that at least can change your expectation a little bit. So I want to talk about education in the U.S. and other countries, and then just a quick overview of calculus. So this was in 1975. This was natural science and engineering degrees per 124-year-olds. So this is something of an indication of how countries are stacking up in terms of technical fields, right? Math, engineering, science. How are we doing in 1975? Pretty good. What about in 2000?
Even better.
So, and these are not just a bunch of like small countries, okay? So these are all major countries here, and so by 2000 we're not doing well, okay? What's this? So what's like the stereotype of a mathematician or an engineer in the U.S.? They're stupid, no? Hopefully not. What's the stereotype? Yeah, antisocial. You're a nerd. You're a nerd, right? So it's not cool to be smart in math, engineering, science. And yeah, hopefully we're making progress in that. But so that the culture and those expectations or labels kind of snowball on themselves, and so then students are hesitant to pursue math and science, and that we just have a bad situation culturally, and culture in the classroom combined with that is leading us to a bad situation in terms of our ability in math and science, or the young people like you that we're raising up. Okay, but now that we're in the internet age, companies you're going to compete with students from all over the world with the internet. Okay, so we need to do better. We need to do better. So there was a study where they looked at 100 randomly selected 8th grade classrooms in Germany, Japan, and the US. They made transcripts of the lessons, they videotaped, made transcripts, and then they took all the cultural identifiers out of those transcripts so that the people who were reading those and taking data had no idea the country that the transcript was from. And so they rated on quality instruction, high, medium, and low. So in Germany, after they took the results, 28% of the class time was high, 38% medium, 34% low, maybe about a third each. Japan had more high and medium, time spent in high and medium type quality instruction. So what do you think it was for the US in this study?
Wait, what?
Okay, so what kind of classroom things is this referring to? So 89% of the time in U.S. math classrooms is spent doing what? What are we doing that's considered low quality instruction in our classrooms?
Just answering this question. Problems that are not based on life applications.
Okay, just doing problems that aren't based on real life. Okay? Busy work. Busy work could be, yeah.
No method to really solve the problem. So here it is.
Yeah.
Tell you how to do it, figure it out.
Okay? What else? You got something?
Well, no, same thing.
Okay, other ideas? Yeah.
You're memorizing instead of learning.
Memorizing, that's a huge part of it. In the back.
How many to rely on tests for your grade?
Okay. What else? Yeah.
Everything is instructors just reading straight off the PowerPoint.
Okay. So just definitions and procedures. that's kind of this study made the conclusion that U.S. is highly focused on memorizing definitions and learning procedures. And that is not engaging in reasoning and mathematical thought. It's just memorizing and learning the steps.
What year is that?
This is about 10 or 12 years ago.
So the phones were not a big issue at that point.
What's that?
The phones and like distractions aren't even an issue.
Actually, part of that study, they did do a thing about distractions, and in the U.S., there were tons of distractions, like announcements and other things, even though there weren't phones, compared to like Japan and Germany, where there are hardly any distractions in the classroom. So that was an issue then, too. Okay, so what about calculus? Is it just a bunch of complicated procedures? You guys know about this?
Yes, I do actually.
All right, so this just does these complex problems for you in an instant. Wolfram Alpha is a website. Here's a calculus question. What is the integral of sine x cosine x from 0 to pi over 2? You hit enter, and it gives you a graphical answer. It gives you a numerical answer. It gives you an expression. As long as your internet's working fast, it's as fast as your internet. Okay? So the question is, why would we take 20 minutes to learn procedures that would take 20 minutes to do something like this if our technology just does it in an instant? Okay, graphing calculator. Here's a complicated derivative. X to the 3 to the x. You can put that in GC, and it'll just tell you the answer. This could take 5 or 10 minutes to solve this. More like 5. But you saw the graphing calculator can do it in an instant. Tell you what that derivative is. So in the past, people that learned calculus needed to do that because we didn't have computers. So we needed people to be able to crank out the answers to problems, be super fast and flawless. Okay, so people were their job was just to do what they were told. But now that we have computers, they can do the procedures far quickly and more accurately. Okay, but the computers can't decide what problem to solve, which function to analyze. All right, so that's where humans come in. Humans have to understand what's going on in the big picture and use technology effectively. Okay, so it's more like managers. So users of calculus today are more like managers. You have to know what's going on. You have to know the big picture. You have to know all the parts and put it together and use technology appropriately to understand a situation wholly. So you need to understand what you're doing and be able to explain why you're doing it, not just memorize and replicate procedures. Okay, so reflect honestly. Honestly, when you worked the symbols and performed computations, to what extent did you understand what it all represented? Maybe some of you did, had a high understanding. But I would guess that there's a good portion that, because of the lead of the teacher, you were just being led along to learn the procedure and then do the procedure with different numbers. Okay, so this class is about developing an expert knowledge of calculus, so you can figure things out, not just remember what to do. That's what we're about. Okay, so if you've had calculus before, that kind of may be a disadvantage in this class, because you may anticipate where I'm going, and you think, oh, I know exactly what's next, and you might tune out a little bit, and then it may not be exactly what you thought. So if something seems familiar, pretend it isn't, and try learning it with understanding and meaning. So kind of pretend that you haven't seen it before. Don't anticipate. Okay, so good math instruction in the US is not good by international standards. It's been proven. And so don't expect this class to reflect a prior math class. So I want to just here's the wake-up call, warning, okay? So again, these are the reason why US is spending so much time with low quality instruction, and we're not matching up internationally. Rote memorization, replicating examples and procedures, doing without thinking, guessing what I want you to say. Okay? Instead, it's about understanding the ideas. That's what I'm interested in. Do you understand the ideas? Developing insight into the world of quantities. We've already started that. Relationships. Ideas come in groups. There's no such thing as an isolated idea. We're going to spend the whole course on the endeavor of understanding the fundamental theorem of calculus. So at the end, when we get to the fundamental theorem, if you paid attention, it will be like, well, of course that's what it is, because we've spent the whole semester building up to the fundamental theorem. Okay? So, tale of two students. Student 1. Rate my professors. Ready? He's honestly a terrible teacher. Nice person. Tries to teach the why and forgets about the how. It really kills your grade. I never have had below a 95 in a math class, and now I'm hoping to get an 88. Okay? So, I'm not sure, but I would suspect that to this student, what is a good teacher? This is what I suspect. Is a teacher who demonstrates and explains complicated procedures really well and then assigns grades based on the ability to mimic them. That's what I would guess where the student is coming from. Okay? But this kind of instruction is putting us toward the bottom in the US. Do you see? This is why we're in the situation that we're at. And you guys have to compete against students internationally when you go for a job. Student number 2 is an email I got. For the first 4 weeks of class, I left every day feeling that my brain had been mauled into abstract obscurity. Now I was actually helping my friend from another college with her homework. She was amazed at how much I knew, and even though all of our language was different, I was able to teach her about the why each piece works and what it is there for. I've also been helping people at my table, and it is so satisfying to having these daily aha moments finally. Okay? So, what does this tell me? It tells me that you can come from this this culture that we're talking about, and you can, in this course, you can make a journey. If you work at it, if you try, if you keep an open mind and you keep working at it, you can make a journey and you can make progress. Okay, so when tackling problems in this course, a common reaction you may have is, he never did one of these before. He never did one of these before. Okay, so we're here to give you the building blocks and tools. Then you'll have to rely on your understanding to solve rather than an example or a procedure to replicate. Okay? You have to bring together multiple ideas we've learned. So we're going to lay the foundation. We're going to give you the ideas and the things that you have to synthesize to solve some of these problems. Transfer knowledge from one situation to a new situation. And write coherent explanations of your thinking. This is the real test to show that you understand it. Okay, you're only going to improve in your problem-solving skills if you're regularly engaging in problem-solving. So if you're going to get better at this stuff, if we believe this is true mathematics, real mathematical thinking, the only way that you're going to improve is if you're forced to do it. Question?
How do you compare as this class between like other classes when it comes to mastery exam? Do you do better or worse?
The mastery exam, so we do about the same. The mastery exam is focused on the procedural aspect of calculus. So it turns out to be about the same. So we still cover that stuff. Yeah. But yeah, the mastery test is only a specific, it's just that memorization and procedure part of calculus. Okay, so you're going to need to get help, and I'll emphasize this again. We've got office hours all week. 6 of us are offering office hours. The 3 that you don't know, the ladies, Stacy, Cameron, and Annie, they're just as nice as us. You've got to just get over your fear and get in there and get help. All right? So use these 6 people that we're offering you office hours all week long. Okay? But when you get help, expect guidance and questions posed back at you to help you figure it out. We're not going to take your problem like you've seen. I'm sure you've all had a tutor that just did the problem, said, here, this is how you do it. It doesn't help you at all because unless you just need to memorize that and replicate it. But you won't be doing that in this class. Okay? So we're trying to develop your mathematical thinking skills and build understanding of the ideas in this course. All right, in terms of grades. So this is a past semester that I had, and this is typical every semester. Here's the distribution of grades at the end of the semester. It's very typical. So this is so work hard, okay? I mean, this is the same as other calc classes. This is the same as most math classes. Okay, so all in all, meaningful learning. It's going to require hard work, patience, perseverance, and help. Okay? This will be uncomfortable for many of you. You're gonna find this is going to be uncomfortable. I'm trying to warn you. You're going to have to work at it and get help. Okay? The benefits are great. Okay? So that second email, she was getting excited about what she was learning. Okay. So where are we at? What time is it? 9:56. Let's look at some more bars. Any comments or questions about that? My soapbox. Yeah, Adam.
You mean contact with your students that went into Calc 2 and 3 that don't experience the teaching style of
Yeah, in Calc, so actually we are working on a Calc 2 and Calc 3 course to follow up with this one. It's in the works. It's in the works. Students that go back to a Calc 2 course that's more traditional have varying experiences. Some find that they can take what they've learned here and apply it and do well. Others hate it. They would rather have it be like this, and so it frustrates them. And others, this didn't make a huge impact, and so they like the traditional. So there's a variety of experiences going on to Calc 2. But we are in the works, or the follow-up Calc 2 and Calc 3 is in the works. And in fact, I'm trying to. I'll hope to teach Calc 2 in the summer. If you come to like this and you want to keep going, I'm trying to teach it in summer B session, July. Okay. So this is the value of one quantity and the value of another. What we really want to start doing now is thinking about quantities changing. And so when we have two quantities, how they change together. We said that calculus could be said that it's a course about quantities. Well, so more specifically, you could say it's a course about changing quantities. So then when the value of the quantity changes. And more specifically than that, you could say that it's a course about how two quantities change together in tandem, two related quantities. So that's what we want to think about. So if I were to increase, given what you see here, if I were to increase the length of the red bar to there, how do you think the blue bar would increase? To which letter there that I posted above? So where do you think in here it would increase? So talk to the person next to you, and then give your reasoning. So we've got some different kinds of reasoning to make sense of this. Don't count squares. Don't try to count the squares on the screen. Just estimate. Okay, where do you think? Let's have some ideas. What do you think right here in the white?
You said between E and F because the red one it kind of doubles, and so it's B
So when she said the red one doubles, what kind of reasoning is she using? She said the red one doubles, so then therefore the blue one's going to double, right? What kind of reasoning is that? Constant multiple or scaling? That's scaling. The red one doubles. The red one is twice its size. So then this one then will also be twice its size. That's scaling reasoning. Okay? What else? So somewhere here. What letter do you think? Gray shirt, right there. Yeah, no, you. Yeah.
I was thinking between F and G and the same reason.
Doubling situation. Anyone use something different than doubling? Yeah.
Well, I think it's closer to H because it more than doubles.
More than doubles. Okay? But still, you still want to talk about how one doubles than the other doubles. Anyone use a different kind of reasoning? Yeah.
Well, we said that if it's changing at a constant rate of change, then it's going to be changed by the proportion that the red bar has changed. Like,
So you're looking at how much the red bar changes,
yeah,
and therefore that's how much the blue bar is going to change.
Yeah, with respect.
That's still scaling reasoning. Scaling reasoning. Anyone use a different kind of reasoning? Okay, well we'll try it here. So let's see. Ready? Here we go. See if you're right. H. Yeah, so it's a little bit more than double. So a little bit more than double is to H. So now I'm going to put numbers on this. Suppose the value of the red quantity is 4, when the value of the blue quantity is 200. And I'm going to increase the value of the red quantity from 4 to 9. So now put some actual computations on it, but still focus on the reasoning. I'm going to increase the red bar from 4 to 9. What will the new value of the blue quantity be? Go. So, but explain your reasoning. And try to do it 2 ways. Try to do it 2 ways. That's what we're about.
9 is 9 fourths is 4, so the value of 9 fourths is 1.
2 approaches. 2 approaches.
That's 1. Now we need a second.
Okay, let's see. All right, so how about, let's go with someone back there. How about, yeah, with your hand up. Yeah, nice and loud. Okay. 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 Okay, so you're looking at the relationship between the 200 and the 4. Is that right? What is that relationship between the 200 and the 4? 1/4? Not 1/4.
Right, yeah, it does.
They're equals.
Okay, so it's a factor of 50, right? Or 1/50th. You could look at it either way. That 4 is 1/50th of 200, or 200 is what? 50 times 4. What kind of reasoning is that? I have the value of the red quantity 4. If I multiply by 50, I get the corresponding value of the other the blue quantity 200. What is that?
Scaling.
Scaling or a constant multiple? It's not scaling. Scaling is resizing the same quantity. Resizing the same quantity. That's scaling. Like you're going to scale up a photograph. So its area is still area. It's just bigger. Or you're going to shrink it down. This is not doing that. This is taking the value of one quantity and multiplying to get. It's not increasing. It's multiplying to get the corresponding value of the other quantity. Right there. 4 times 50 is 200. That's constant multiple reasoning. So therefore, if I'm going to change the red value to 9, how would I calculate the new blue value? I'm going to change it to 9. I'm going to divide by 50? Multiply by 50. All right, so if I multiply by 50, I get? That was supposed to go over here. So we're going to take 9 times 50. And you get 450. Constant multiple reasoning, okay? What about another way?
Okay, so the way I did it is I took 9 minus 4. I took the difference, so just 5. And I know for each one of them, for each one of the red bar, it's equal to 50. So
Okay.
I multiply 5 by 50, just equal to 250.
Okay.
And that's the difference it's going to change by. So when we add the 250 to the 200, we get the 450.
Okay, you're still kind of doing this. You're still using this. You're using that factor of 50 to do it. Yeah.
So for constant multiple, what you're doing first is looking in terms of like comparing the 4 and the 200
Yes.
before you compare the 4 and the 9.
Yeah, the constant multiple means you've got the value of one quantity. That constant multiple will give you the corresponding value of the other quantity. So 50 is the constant multiple. So we're going to use that constant multiple to figure out what the corresponding value to 9 is. So another way to do it. Adrian. Okay. So what did you get? 2.25. What's that? What kind of multiplier? So what is it doing? That's scaling, right? So that's increasing the size of this quantity by 2.25, by 2.25 times as much. Therefore, if we start at 200, what are we going to do? Also times it by 2.25, which gives 400.
So that's scaling now.
That's scaling.
Side, you're scaling the other side.
Right, so we're looking at how much did the red, by what factor did the red quantity change? By 2.25 times as much. So then the blue quantity is going to change by the same amount. Scaling. Scaling. Does it make sense?
Yes.
Okay, let's change it up. So now I'm going to give this some meaning here. Let's take these off. And this one is going to be the volume of water in milliliters in a test tube. And then this will be the height. The height of the H2O in centimeters. Okay, I want you to estimate, don't count squares, estimate the relative size of the blue quantity, the height of H2O, with respect to or in relation to the volume of water in the test tube. So to have a conversation, what's the relative size of the height of water in the test tube in relation to the volume of water in the test tube? Go, have a conversation. What would you estimate the relative size to be? Go. Okay, what do we think? Let's see how it's. How about right here in the tank top, the white tank? What would you the relative size of the height in relation to the volume? She says it's 1/4 of the volume. The relative size is 1/4. What do you think? That's it. That's it. The length of the blue bar is 1/4 relative to the red bar. So now I'm gonna put more water in the test tube. Too much. Okay, so I put more water in the test tube. Was the relative size maintained? Just by eyeball. Sorry, too much. Is the relative size maintained? Yes. Yes. Okay. This test tube has straight sides. So the height is always 1/4 of the volume. Okay, I just want to warn you. I need to go a couple minutes over today, just so we can get through something important. So I'll try to give it back to you on another day. Is that fair?
Yeah.
Okay.
Yes.
Thank you. Okay. So what I'm going to do is I'm going to take the blue bar and I'm going to turn it on its end and I'm going to stick it on the end of the red bar. Okay? Watch. You ready? Can you imagine that? Didn't change the length of it, so it's still this 1/4 relative size of the height to the volume. Okay? Then I can choose a different amount of water, keeping the blue bar and that relative size is maintained. So what happens is, if we were to, come on, where are you? Let's put a set of axes on this. And what we get is we look at a volume of water and then the corresponding, oh, but we got short passing periods today, don't we? Okay. So you get the corresponding height, and that gives you a point. And so the coordinates of this point are 4.65 milliliters. And how would we calculate then the height corresponding to 4.65? Yeah, if the relative size of the height to the volume is 1/4, then we're going to take 1/4 of the volume to get the height. So it's going to be 1/4, because 1/4 is the relative size. So we can imagine then, starting at 0, no water in the test tube. Maybe. Here we go. No water in the test tube. And we can imagine filling the test tube with water, and what's going to happen? As the water fills up, the height is going to increase, right? And so how many points are we going to get like this one? How many points are we going to get like this one as we let the water fill up? An infinite amount, right? Okay, so it's like, have you seen vapor trails on planes? So let's put a plane on the top of that with the blue bar. And let's give it a vapor trail. Oh, where's the vapor trail? There we go. So it's leaving behind all of the points that you would get as the water increases and you get the corresponding height. Okay? So when you see a graph, last thing, I'll let you go. When you see a graph, you want to think of a graph like this. That a graph is a set of points. Okay? It's just easier to draw it this way, like a curve or a line. It's harder to draw every single point, right? It's too time consuming. So when you see a graph, what do you imagine? You're imagining, you're imagining this, that it's a set of points, each one representing two corresponding values of two quantities. Corresponding values of two quantities. Each point represents corresponding values of two quantities. The graph then is all of those points. Have a great weekend.